Welcome, everybody. I'm Giovanni Merlino from University of Messina. I'm going to present an edge computing case study for Monasca, actually a smart city AI-powered surveillance and monitoring use case. A few words about me. I wear several hats, here just a few, as postdoc member of the MDS Lab research team at the University of Messina, for short UNIME. Member of the ICT staff, still at the University of Messina, also involved in the hashtag SmartME crowdfunding initiative to turn Messina into a smart city. And last but not least, co-founder of the SmartME.io startup company. In terms of research and development in ICT, the MDS Lab, together with the ICT staff at the CIAM, University of Messina. Here you can see also the staff involved specifically in the Stack for Things and the whole Smart City project, and some research activities and services that are provided. In particular, we are very active in the cloud computing and IoT edge space. SmartME.io, this is the startup company. Actually, it's a spin-off company, an academic spin-off actually from the University of Messina, in the sense that it is incubated in the university, focusing on smart city solutions. And one of our mottos is that we want to build this stuff on a shoestring budget, because that's what our customers ask. So we are also quite small, but a very dedicated team. Also, what's important is that we have a lab in Messina, a smart cities lab, which belongs to the CINI, which is the National Inter-University Consortium for Informatics in Italy. So that means that Messina is quite front and center in these activities related to smart cities. Okay, brief outline. After the motivation, we are going to spend some words on what cloud and IoT integration means for us, the enabling technologies, and in particular the architecture of our so-called Stack for Things framework, our solution, the smart city pilot and case study, including a demo, the functionalities and the service levels supported, also in this case including a demo, the application domains, and some words about the future work. In terms of the motivation, we all know that we want to tame the complexity and the heterogeneity of IoT systems, IoT devices. For us, the IoT ecosystem includes quite a number of disparate systems, which go from mobiles to smart appliances, systems like standalone sensors, actuators, wearable vehicles, in general, what are typically called cyber-physical systems. More in detail, we can at least mention three useful categories, like microcontroller boards or single-board computers. In particular, in the case of single-board computers, they are becoming very widespread. Their popularity is exploding, typically endowed with sensors and actuators attached, for instance, to GPIO pins or any of the buses, and typically support a wide range of interfaces. Then smart objects, more in the general sense, because we're talking about typically stuff which can be considered kind of consumer appliances, like, for instance, the smart home kind of technologies. Typically, also in this case, we have a range of connectivity options. Even more so in the case of smartphones, which we know very well, typically are equipped with a long list of sensors on board. Now, in terms of the cloud and IoT integration, we, let's say, have identified at least three approaches. One we call data-oriented approach, which is, let's say, the most mainstream approach. which features IoT devices sending data to the cloud, applications which are built on top of standard cloud facilities, VMs, storage, network facilities. The application which typically makes use of stored, somehow non-real-time IoT data. And anyway, any kind of interaction, for instance, if we think about commands, so possibly actuation, typically is indirect, IoT device initiated only. Another kind of approach we call application-specific, also vertical approach. In this case, you have that typically applications use ad hoc mechanisms to interact with IoT devices. There are no explicit interactions with the cloud, between the cloud and the IoT infrastructure. And so typically, it is meant to be a sort of a static infrastructure deployment. Our view, instead, is a sort of what we call a full IoT cloudification. It's also what we called in a recent article in Computer Magazine, the IO cloud. The idea is that we consider IoT infrastructure as a natural extension of a data center. So we want to provide well-defined cloud API as a resource management interface. We want to keep the ability to separate concerns when needed, of course, between infrastructure and application. Somehow this goes in the direction that many are calling for, so from the cloud to forward edge computing. And the idea is, of course, to leave the door open for device computation offloading. Now, the main issues, because there are quite a number of differences between classic infrastructure as a service cloud and this kind of IoT extended cloud, that IoT devices, of course, are resource constrained, very resource constrained. Typically, they are, of course, out of the data center. They are typically at the edge of the internet and most times behind some middle boxes, network address translators, firewalls, and so on. Are, of course, unreliable by default, somehow, with regard especially to networking and computation capabilities. They do not have some, let's say, standard data center facilities, for instance, out-of-band, lights-out management systems. Also, and that's also very important, IoT devices do not belong to the same administrative domain. There is a difference here between a cloud administrator and a resource owner. The reason, the resource owner can be any private citizen, a sort of voluntary contributor. So Stack for Things is our answer in terms of the solution, in the sense that Stack for Things embodies our approach, our IO cloud approach. The underlying technologies are, of course, OpenStack, WAMP, Node.js. Now, in terms of Node, the reason for mentioning it is because actually we don't have just one implementation of Stack for Things, but two. The erstwhile is what we call a standalone implementation. It is based on Node. Here are a few words about Node, but I won't delve into that. What's interesting is that the Node is quite popular in the IoT community because there are a few frameworks like Node-RED, Cylon that are focused on that domain. The erstwhile, as I said, the implementation, because the idea is that there we somehow played in a sandbox our ideas from the research that we were conducting. The OpenStack-based implementation is sort of trying to make it scalable, production-ready, and trying also to integrate with other subsystems and other communities. So we're talking about IoT resource management. We are talking about a specific service for that in OpenStack. It's actually an unofficial project. I don't know if it's right to call it an incubating project because it is available in both Launchpad and Git openstack.org. You can download it. It is aligned with our own repos. The WAMP protocol, that's very important because that is, by the way, first of all, an open standard. It is a messaging protocol. It is also a WebSocket sub-protocol. The idea is that you can have, with a unified protocol on the wire, two application messaging patterns: publish, subscribe, and RPC. Now, of course, for this community, it's obvious that we know very well that AMQP is the standard de facto in the data center. But here we are talking about having WebSockets as transport and trying to have this kind of capabilities. For instance, if we talk about RPC, it is not supported in IoT typical environments. Let's talk about MQTT and stuff like that, okay? The high-level overview of Stack for Things, this is the IoTronic on the cloud, the cloud-side subsystem, which interacts with other OpenStack services. Of course, it has its own command line client as the other OpenStack services. And there is an agent. We call it here also probe, which stands on the device side, on the IoT board, on the node, on the edge node, which is called Lightning Rod. So Lightning Rod actually acts as the point of contact between the board and the cloud through a number of communication facilities. First of all, there's a control channel, which is based actually on WAMP. And there is the option to instantiate a number of WebSocket tunnels, WebSocket-based tunnels, for either virtual networking services or even service forwarding services, but we'll see in a moment. Okay, a few words about the Smart City. The SmartME project, you can notice that, of course, it reminds you also about the name of the company. The reason is that historically, that started first. The SmartME project with the hashtag in front of it, it was a crowdfunding initiative, a successful one, by the way. It was a collaboration between the MDS lab and some key actors, worth mentioning, apart from, of course, municipality and other interested parties, Arduino Labs. The reason is that actually SmartME IO is, let's say, the heir to the previous company which was incubating in our department, with most of the same colleagues, which was the first Arduino lab from arduino.org, before everything folded. Maybe you know the history behind Arduino. I don't want to bother you with that. Anyway, also a platform for experimental testbeds, of course. That was the original idea. Now, here we can see just a very I mean, the first example of a SmartME node. Now, it is not the only one. We use also other kind of nodes, as we'll see in a moment. But this was the first deployment, let's say, the first wave, with the Arduino Yun, a shield, and a number of sensors. I won't go into much details about this stuff because apart from the slides, which I will, of course, upload into our page, you can find lots of information on the portal as well. The current implementation, that's important. As I said, the Arduino, of course, the kind of Arduino which is powerful enough to host this kind of agent. Actually, it is an MPU-MCU combined board. But we are also support the Raspberries and similar kind of devices. Okay, we support, I mean, I can also run on my laptop, I did. But what's interesting is it's also supported on Android, which you know quite well as certain strict requirements, certain limitations due to, of course, to security. But we have a preliminary implementation working also there. Now, this is the architecture of the SmartME framework. So here we are talking about the Smart City solution. Now, the Smart City solution, of course, has both an administration portal, an administration surface, which of course is powered by Stack for Things. by the Stack for Things cloud. Then there is also the public portal, so where citizens can consume data. And of course, in this case, we have what we call our data plane. Now, the data plane here is, let's say, the first version of SmartME, where there was a CCAN data store, an open data store, and accompanying CMS. Obviously, that's not the end of the story, because actually we were working specifically with Fujitsu. And by the way, today there should have been also our colleague from Fujitsu, Cristiano Bellucci, but he didn't join at the last moment. The Monasca subsystem, which is for, as you know very well, for monitoring and logging, is something we are integrating in our solution. And specifically, we have our own deployment, which includes specifically the InfluxDB as a database for the actual data series, time series data specifically. And of course, the idea is to use it for a number of other duties. I won't bother too much on the Monasca side, because actually we had a talk last year in Boston mentioning more specifically the details about the Monasca side. So I will focus now on the use case and the Stack for Things. In particular, the data I was mentioning, which is going to be stored in the InfluxDB in Monasca, is in this case surveillance data. But which kind of surveillance data? The problem is that if we talk about surveillance, of course, it can quickly become scary. Now, the idea is that, of course, we don't want to scare anybody. We actually thought about this SmartME CAM product and service by talking with our erstwhile customers, like, for instance, the Catania's airport in Sicily. And the idea is to be as privacy preserving, as privacy sensitive as possible. So in particular, the idea is that the edge node goes here in the local private network where there's a EP camera, if there is, but even if there is a legacy CCTV system, the idea is that once we put the board there, of course, there are a number of options also in this case. Specifically, we are talking both about the Raspberry Pis that we are using, but also more specialized systems where we need, as we'll see in a moment, some further computation. In particular, NVIDIA Jetson-based systems. When I talk about NVIDIA Jetson, in fact, is because we want to to execute machine learning, deep learning algorithms. So in that case, we need to have that kind of power, but we are still talking about an edge device, and we are still talking about the fact that the video stream doesn't leave the edge device. So no way to, let's say, inflict some privacy issues on the customer. Now, quick demo time. Okay. No, you can't see that. Just a moment. Ending show. Now you see that. Okay, that's just a quick view of what we have. We have a customized dashboard where we have object detection. Now, what's important is that the software runs, I mean, for object detection, which is deep learning based, runs on the edge device first. Second, the data here, the only data that gets transferred to the database, to InfluxDB, is the object count and the object positions. And okay, I can also show you here, okay, here is Grafana, so we can have, of course, our object count as well, which is still powered by the Monasca stack. But what's interesting is, of course, we don't want to be bothered with the kind of deployment that we have. Just in a moment. because the issue we have is that the typical deployment scenario can be like that, as we said, no? So the problem is we want to be sure that we are able to reach the dashboard, which is local to the device, and of course, at least if we want to inspect the video stream, but of course we do that on demand. What we need to do is to exploit the networking services, which we are going to see in a moment. But first, if you remember, we talked about device-side enablement, in particular the requirements. So how to deal with the fact that we have no out-of-band lights-out management hardware? The idea is that, of course, Lightning Rod needs to act as a software counterpart of such management systems. So it means it is always running, of course, but it means also it has a kind of watchdog-like behavior, always remotely accessible at the lowest level, e.g. console-like, for instance, and sandboxed where possible, because we want to be sure that no other process messes up with our control. Now, on the cloud side, a few words. We said that IoTronic is a OpenStack compliant subsystem. Actually, it is modeled after IoTronic. Obviously, from IoTronic, maybe you have noticed the similarity. We have, of course, the Horizon dashboard, which is our control surface, and it is, of course, customized for that with a specific panel for the IoT. We have a deep integration with OpenStack because, as we said, it's modeled after OpenStack interactions, is implemented as OpenStack service, and we want to leverage OpenStack facilities as much as possible, and we'll see in a moment. This is indeed just the IoTronic part of the stack. We see that the architecture is typical with a conductor and a number of agents communicating over AMQP. More in particular, what's important to notice is that we have a WAMP agent and a WebSocket tunnel agent. And in the case of the WAMP agent, of course, we can have more than one, as well as for the West tunnel agent. They control a WAMP router, which is actually the broker for the messaging system. Now, in terms of networking specifically, Neutron is exploited to create virtual networks. In particular, the idea is that we want to be able to achieve this kind of, say, connectivity, which goes from the board to the cloud, but also to other boards, and includes, of course, any kind of workload. So let's say a standard plain VM on the cloud. What happens is that on the device side, we use WebSockets. We use even other Linux low-level tools, for instance, Socket for the creation of virtual instance interfaces. And virtualization is both at the network and the data link layers available to enable, of course, any kind of flexible topologies. The idea is, of course, we started from that because we wanted to be totally agnostic from the infrastructure from the point of view of applications. For instance, we have used some, pilots based, for instance, on service discovery protocols like AllJoin. And in the case of AllJoin, we had to be on the same broadcast domain if you wanted to have this kind of service. In our case, we did it on a wide area network. This is the architecture on the cloud side for Neutron, for the Neutron integration. So we see that we have in the green dashed line, we have the Neutron controller, and we have the Neutron nodes on the right with the dashed orange line. The idea is that we have, of course, as we said, the tunnel agent. We have the L2 agent, which is meant for, let's say, the boards. And we have the connectivity, which is based, as we said, on WebSockets, and more specifically on VXLAN overlays, which are tunneled over WebSockets. This is the node-side architecture. And we can see that on the right we have the virtual interfaces. We can have, of course, more than one. And the structure in the purple square is about the various modules comprising the agent. There's Lightning Rod engine, but then there's West Tunnel plugin, there's the WAMP library. And we also have a plugin loader that we'll see in a moment. I will skip details about the lower level part because that is specific to the environment. In this case, for instance, a combined MPU-MCU system. In terms of topology and datapath, we have, as we can see, the tunnel agent node on the center, the board on the right. We can see the kind of bridges which has to be available. In particular, we can see the presence of the VNI for the VXLAN. And we see the usage of socket to actually expose the interface and the port respectively on one side and on the other of the pipe on the board. Here we can see just a couple of diagrams depicting some scenarios. So same board instances, same overlay. And in this case, that means that on a tunnel agent node, there is a shared Linux bridge. The case where you have same board instances, but separate overlays. And in this case, two different bridges. Now, also, some words about the fact that we said that we want to meet IoT peculiar specific, let's say, requirements. So in a sense, from the start, from the get-go, we had a look also at something that we can identify as crossing the, let's say, the layers between infrastructure as a service and platform as a service, because in particular we support also what we call plugins, so a kind of plugin-based development. The idea is that we use plugins as self-contained, minimal, high-level code units, so there is a design time advantage, but also as isolated sandboxed processes, so there's a runtime advantage. The enabling mechanisms are, of course, wrappers for runtime execution, plugin registration on the cloud, plugin injection, so deployment on the fleet of devices. Of course, you can understand that this somehow mimics what you can obtain with containers and other more advanced stuff, but obviously the problem is that you are not always able to have containers in the platform that you are targeting. So this is our, let's say, very quick and dirty answer to that. Demo time again. Now with the platform. So let's see first. You can see there's IoT panel. Sorry, got logged out. Okay, you can see the boards here. Here we have a Raspberry. It's, okay, classified, it's mismatch, it's a server, but it's actually a Raspberry. Status online. Okay, first of all, let's do, I didn't clear it up, so let's do it. I'll now enable a service, what I just removed, SSH. What I've done is I've exposed this over this port and that IP, the SSH So let me see the port, 6186. Yeah. There, I'm in a Raspberry Pi, actually. Okay, you see the interfaces here. In particular, you can see that the only interface, okay, no, I need to clean up another stuff. Actually, I already attached the port. I'll detach and retouch again so you can see and follow. So first of all, what I did until now is service forwarding. I have opened the port and forwarding from the cloud. Now, you can see the only interface which has an IP is this one, and it's a local area network IP. What I'm going to do now is attach a port. That means, OK, I use this network. In the meantime, let me see what I have here. This Vancouver is a Sear OS VM. You see, this is the IP it has been assigned. OK, already done. It was too quick for me. You can see here, this is the IP it got. Of course, OK, you can see the reverse. If I detach, I will lose the ping capability, of course. There. OK. Then a couple of words about about the plugins. Maybe I'm running out of time. I want to be sure that I have time for your questions. So I will skip to the final words. OK, these are some application domains, of course. So interacting cyber-physical systems. We talked about smart city, but we are already targeting smart home, smart building, also industry 4.0. In terms of smart communities, makers was the first, let's say, constituency. But then meteorologists, we're talking about environmental monitoring in the case of the SmartME earliest erstwhile work. Then safety and law enforcement officers, that's the case of surveillance. And the list grows day by day. Fleet management, of course, that's what we are trying to do first, software upgrades for fleet of products. These kind of scenarios, so security surveillance, we also have some other stuff like vehicle position tracking and so on. Now, in terms of future work, that's very important for us. We want to spin some built-in functions of IoTronic, of course, into other more apt subsystems, because we want to break it down to its core. We like the Unix approach. We want one tool doing one thing only well. Specializing it for IoT unique, not applicable, or uninteresting features to the other communities in the infrastructure and platform space. So in terms of further interaction with OpenStack and its communities, we were looking even in these days in quite a few interesting achievements and developments in the community. For instance, if we talk about the placement API, so trying to have traits, specified traits, I mean, for the boards, according to available physical resources, something which happens similarly for virtual GPUs. Mogan, which is a way to somehow abstract the kind of functionality that you find in IoTronic. The idea is that IoTronic could become a bare metal provisioning driver for Mogan, for IoT resources in particular. Keystone, also very important, authentication, authorization, and especially delegation mechanisms dealing with the IoT different administrative domains and ownership models we identified. So actually, in this case, we're working on that, on research. We're formalizing that. And also, we are trying to play with some kind of very, let's say, hot technologies. At the moment, we are also working with blockchain, and we think that maybe it can fill an interesting place in this community. And that's it. Thank you very much. And by the way, a shout to our devs and collaborators, because demos wouldn't be possible without them. And if you have any questions.
Go ahead. How do you manage the configuration of the sensor devices, like putting Raspbian on it and all of that?
Okay, you're talking about manipulating the sensors and actuators. I didn't show, because there was not much time, the plugins. But the idea is that, for instance, with plugins, we can inject a runtime snippets of code that can interact with the sensors and actuators. Typically, what happens is, for instance, with GPIO, you interact over sysfs. Indeed, we used that same kind of abstraction, level of abstraction, because we are very interested in the developers and so the kind of platform as a service, that we worked also on our, what we call drivers in Stack for Things terminology, which is a way to have control logic to map certain resources in sysfs from, let's say, of course, a path to another. But inject in that some specific logic. Let's say you have temperature, you have a certain voltage, and you want to get that, let's say, transformation of that value straight away from the file system. You can get that with drivers. I didn't show because there wasn't much time for that, but that's developed as well.
Okay, thank you.
So it's a quick question regarding you're running the agent on a Raspberry Pi or Arduino boards. Have you measured the footprint overhead of those? How much compute resources is like just that agent will take?
The agent is very, very, let's say, very lean in terms of resources. It doesn't max out the resources, even on something which is very, very constrained. You have to consider that we have the agent running also on the Arduino Unes, which are, let's say, our lowest level kind of device, because in terms of resources, it's only 64 megs of RAM. And it has, we can even let it run from the flash, not adding any USB or other external mass storage device.
But for the web socket, you pretty much have to implement that entire stack, right, over on those devices.
Yeah, of course, what's important is that the agent at the moment requires at least a Linux-based, even if very, very minimal environment. Like, for instance, in the case of the Arduino Uno, what you have is an OpenWRT-derived kind of environment.
I see.
We also are working on enabling microcontroller-only devices. But there, of course, there are other constraints that needs to be worked out, of course.
That would be really cool if those things could be running on a microcontroller stuff.
Yeah, yeah, sure. Specifically, we were working on STM32 at the moment.
Ah, okay, cool. All right, thank you.
You said that you have customized the Horizon. Is it a fork branch, or you have implemented a plugin for Horizon?
It's a panel. Yeah, yeah. You find everything in the repos that are available on both Git or OpenStack.org. Also, of course, they are also available on our own organization, GitHub/MDSLab. Of course, I didn't say it, but at those links you can find everything. Actually, we are at the moment working also on updating documentation, because that's typically the last step in making stuff out. So it's there, documentation, but it's a bit outdated. We are working on updating that.
And regarding integrating with Monasca, have you used any standard Monasca agent, or you have implemented?
Yeah, standard Monasca agent. We also worked with some other, let's say, custom agents somehow, which was not Monasca specific. That was last year. Now I don't remember the name actually. What's important is that the part about Monasca is important for us, but is of course the data plane. This is the part of what we call the control plane, because we like to keep them separated. Because one is, let's say, what we call somehow the platform, as the case of the plugins. For instance, last year, actually, the agent for Monasca was deployed as a plugin, to be clear about what is the kind of objective.
Thank you.
So what do you think your scale limits are with your approach?
What are the?
Scale limits. So, for example, how many sensors, how many Raspberry Pis, what are the resources to control a city full of Raspberry Pis? Or
yeah, at the moment, our main deployment is in Messina, and it is not such a large deployment. We're talking about 100 or more devices. The fixed ones, of course, there is mobiles as well, but that's students or faculty staff, not that many people. What's most interesting about your question is that we'll soon test the scalability limits of the system, because now they awarded our practice in Messina as a best practice for the nationwide contest there was in Italy. So it's going to be reused in other big cities, bigger than Messina, in Turin, Padua, Lecce, and Syracuse, very, very soon. So it's going to be large very soon.
But how many resources do you use for what you're managing today? Like
on the cloud, you mean?
Yeah, yeah.
Well, standard servers, and then not anything special, let's say. Plain data center servers, but just, let's say, one. Actually, you can, of course, install IoTronic on your laptop if you want. Yeah. It's totally possible. Okay. Okay. Thank you again, then.